Why no one is in costume? Okay. Oh, that's your costume. I see. All right. So let's look at this problem. We have a heat engine that operating on a Carnot cycle. So that means that this heat engine is an ideal engine, so which is reversible, has a thermal efficiency of 75%, which is pretty high. So when we have a heat engine, and which is an ideal heat engine, in other words, Carnot heat engine, there are two ways to determine their efficiencies. The first one is desired output, W dot out, over required input, Q dot H. Or you can say, this one is 1 minus Q dot L over Q dot H. So that's what we studied for conventional heat engine. Now, we say that this is a Carnot heat engine. That means that the efficiency can be also calculated by reversible heat engine, which can be done by 1 minus TL over TH. And when you do the calculation, it is 75%, 0.75. So the waste heat, which is Q dot L from this heat engine, is rejected to a nearby lake at 15 degrees Celsius. So this is the temperature of the low temperature thermal energy reservoir. So this one is 15 at a rate of 14 kilowatt. So this one is 14 kilowatt. Determine the power output of the engine and the temperature of the source. Since we know the efficiency is 0.75, from this equation, you can determine Q dot H. So if you do, Q dot H is going to be 56 kilowatt. So this heat engine observed heat at the rate of 50 kilowatt, 56 kilowatt, and reject a heat at the rate of 14 kilowatt. So what is the power this heat engine produces? The difference between Q dot H and Q dot L, which is 42. W dot net is going to be Q dot H minus Q dot L, which is 56 minus 14 is 46 kilowatt. Then, what about the temperature of the source? The temperature of the source is this TH. Since 1 minus TL over TH is 0.75, we can determine TH. However, there is one thing that you need to be careful, which is you never use degrees Celsius. So this one is 288 Kelvin, and you can determine TH, which is 1152 Kelvin. That's how you solve the problem. Any question? Right here, we have two more questions before we complete chapter 5. This time we have a heat pump operates on a Carnot heat pump cycle. By the way, maybe it will be better for me to give you a summary of what we studied before. So when we have a heat engine, this heat engine has two thermal energy reservoirs. One is at high temperature, the other one is at low temperature. We transfer heat from low temperature to high temperature. I'm sorry, we are observing heat from high temperature at a rate of Q dot H and produce power, W dot net, and any remaining heat is going to be rejected to a lower thermal energy reservoir. That's heat engine. What about refrigerator? Refrigerator also has two thermal energy reservoirs. One is at high temperature. The other one is at low temperature. We are pumping heat. We are observing heat from low temperature and release that heat to high temperature at the rate of Q dot L and Q dot H. And to make that happen, we supply power. What about heat engine? It's the same thing. Heat engine has heat pump has two thermal energy reservoirs. One is at high temperature. The other one is at low temperature. We transfer heat from low temperature to high temperature, which is against the second law of thermodynamics. So to make that happen, we need to provide what? Power, W dot net. In this case, this PR of this refrigerator is the refrigerated space. And TH is the kitchen air. On the other hand, TL is going to be outdoor and indoor for heat pump cycle. So how can we evaluate their performances? For heat engine, we use efficiency. Desired output, we want to produce power. Over required input, we need to provide heat. For refrigerator, we can use COP. For heat pump, we can use COP. Desired output is going to be the heat transfer from refrigerated space, Q dot air. To make that happen, we need to provide power. What about the desired output for this heat pump? We want to heat inside, so the indoor Q dot H is the desired output. To make that happen, we need to provide power. And since the energy balance equation is W dot net is Q dot H minus Q dot L, so we can replace this W dot net with Q dot H minus Q dot L. If you do, the efficiency is going to be 1 minus Q dot L over Q dot H. COP of refrigerator is going to be Q dot L over Q dot H minus Q dot L. The COP of heat pump is Q dot H over Q dot H minus Q dot L. So that's how you evaluate the performances of these three cycles. Now, if it is a Carnot system, which means completely reversible, the efficiency can be determined by, which is reversible, 1 minus TR over TH. COP over refrigerator, which is reversible, can be determined by TR over TH minus TR. So you're basically replacing this Q with T. What about this heat pump? COP of heat pump, which is reversible. It's going to be TH over TH minus TR. So that's how you evaluate these three cycles for the actual systems, for the Carnot system. based on that, let's solve this problem. You can write them down on your formula sheet, right? You don't have to memorize them. Write them down on your formula sheet. By the end of this semester, make one very well-made formula sheet from chapter 1 to chapter 9. Then you can take this one, laminate it, and take this one for your career, throughout your career. So whenever you need to, review thermodynamics, don't read 1,000-page books. Read that formula sheet. That will give you the idea how to solve that thermodynamics. A heat pump operates on a Carnot heat pump cycle. So which means that this one and that one. So let's just write down the COP. COP of heat pump can be determined by this equation. Q dot H over W dot net, or Q dot H over Q dot H minus Q dot L, or since it is a Carnot heat pump, we can also use this one. TH over TH minus TR. And the COP is 8.7. That means if you spend 1 kilowatt of electricity, you can provide 8.7 kilowatt of heat transfer rate to the house. So this is 8.7. And the temperature of the indoor temperature is 26. So this one is 26, right? No, 299 Kelvin. By consuming 4.25 kilowatt of power. 4.25 kilowatt of power. Determine the temperature of the reservoir from which the heat is observed. That means TR. The heating load provided by the pump. That means Q.H. Can you do that? Yes, you can. Pretty simple, right? So if you calculate this one from this part, 264.6 Kelvin. If you get this one from these, you get 37 kilowatt. Any question? This is the last problem of chapter 5. And we can go to chapter 6. No, chapter 6. Yeah, chapter 6 is also in the exam, not the second exam, the last exam. So we can finish this problem today. That means we can have an exam the following Thursday. So our exam is going to be the Thursday. Why? Chapter 5? Exam. Yeah, I know. Exam is stressful. You get less stressful if you prepare more, right? If you prepare good, you get less stressful. So if you are stressed now, that means that you're not prepared. So study harder, okay? So one day you get no stress. That's the day you need to take the exam. Why? You need to make sure that yourself is ready by Thursday, okay? Okay, so for a brief minute, let me give you, the best way to prepare your exam. Studying thermodynamics is super easy. It just takes time. So you need to spend more problems than your friend by the exam. So how can you solve more problems than your friends? Because you got the same, the limited time. You only have 24 hours per day, right? The same as me. So you need to solve whenever you have time. Like when you get up in the morning, what do? Solve a problem on your blanket. When you wash your teeth, solve a problem on the mirror. While you're eating, solve a problem on your another plate. But if you have some rices, count them. No, I'm kidding. When you drive, come to the campus. Of course, do not solve a problem. But once you park, there's a windshield. Solve a problem on the windshield. When you come into the building, you may go to the restroom. While you're peeing, solve a problem in front. If you keep doing that, you will get stress-free. And then you will desire that I want to take the exam as soon as possible because I don't want to live this life. See? Then you will get 100. Are you planning to take heat transfer next semester? I won't be there. I won't be there. Dr. Walter Malik. Why? Okay, so it's a good time to meet him, right? Yeah, he's good. He's good. He has a lot of, the industry experience. Otherwise, you have to wait until the following spring semester if you want to see me in heat transfer class. So you need to see, the Dr. Malak. I think he's teaching this one. I'm not sure. I'm not sure. I actually don't care because I won't be here. So somebody is gonna teach that. I will be on sabbatical. Every 6 years you get, a year off for your research. Solar power plant. So I design a hybrid material that can store more energy than the conventional energy storage systems for solar power plant. Interesting, right? Because solar power plant, everyone talk about solar. Can you use the solar energy to turn on this light right now? No, you can. There's raining outside. So what do you want to do? Storage. So what kind of storage? Battery systems? Yeah, you can do so. If you buy 1 million Tesla for this Mount Pleasant, you can, the store electricity, for Mount Pleasant. Do you have that much money to buy 1 million Tesla? No. And, every 4 years, you need to, to buy a new one because the lifespan of, the electric battery system goes down. So what do you want to do? You want to store electricity as is? No, you can store energy in another form. Yeah. Well, when you collect the sunlight, you can produce electricity right away by using photovoltaic system like a black panel that you install on top of roof. Or what is the form of energy coming from the sun? Heat. So you can store heat and use that heat to run a power plant later. Storing heat difficult? No, not at all. Is it expensive? Not at all. So you can store heat as, in the form of heat. So we usually use a table salt, like a molten salt. So you melt it, it becomes like a water, but at extremely high temperature, 600 degrees Celsius. You store that, and when, the sun goes down, you use that heat to produce steam and then run the power plant. That is called CSP, different from PV. You heard about PV a lot, photovoltaic system. Because what is the customer for photovoltaic system? You. You can install, the photovoltaic system on top of your roof, making your house ugly, right? But can you install CSP in your backyard? No way. How much is it? Usually $1 billion or so. So it's not B2C business. Photovoltaic systems are B2C businesses. So that's why you get a lot of news, a lot of the information, because you can be a potential customer. CSP is a B2B business. If you are working for CSP company, do you care you know about this technology or not? We don't care, because we are selling them to a country, to a state government. So they don't do any advertisement. So you don't know them. Have you heard about CSP? Not much. Let me show you just one figure, because we have plenty of time with just one problem left. Let me show you one figure. CSP, there are many of them. I'm going to say one thing. Ivanpah, solar electric generation station in California. Oops, oh, my Pepsi. Click image. How can I enlarge this one? Open in a new tab. So this is the CSP system. 40 minutes west of Las Vegas. Each meter is reflecting the sunlight into a focal point. So we generate heat at 1000 degrees Celsius. We pump salt back here, make it liquid, and then put it back, run the Rankine cycle, the heat engine cycle, to produce electricity. Each meter is bigger than this classroom. To the sun, sunlight coming back to here. Have you seen it? No, because you are not a potential customer. State government, federal government, so usually each of them is about $1 billion. Yeah. Not each meter, the entire power plant. So where this electricity goes, I just told you it's 40 minutes west of Las Vegas. It goes to Vegas. We have about 50 or 60 of this one in United States, usually in the the hot area, Nevada, New Mexico, Arizona, and California. Have you seen it? No. Because why is that? It's all business reason. You're not a customer. Yeah, you can go there. You can go there, you can drive there. If you go to European countries, you see more and more of these plants. One of the most famous one is Gamma Solar. That's what I was trying to explain. So this one, let me show you. Open in a new tab. So this is the main tower, and these are the meters. This is not completed yet. It's one of the construction. So they focus the sunlight into a focal point. It's usually on top of this tower, and then there is the fluid. We need to store that energy. Are we going to store that energy in battery systems like Tesla? No, we need to buy billion Tesla. How much is it? So these are the tanks. High temperature thermal energy storage. Low temperature thermal energy storage. You remember heat engine that we studied. So this is the heat engine. There's a power conversion module. There's a turbine, condenser, etc. This is a hot tank. This is cold tank. So we store that high temperature energy here at night, here in the daytime, and then at night, this one goes in to run this power plant. So the power plant runs 24 hours. Is it a commercial scale? Yes, it's commercially operating 24 hours. Then why don't we know them? Again, we are not the potential customers. Interesting, right? Because everyone talk about, the solar. You just come up with this black panel. That's good. Black panels are good if you can spend all the electricity that you generate right away. But you want to spend electricity when? When the sun is down. People are, investing a lot of money to, develop, the more efficient battery systems, but that's not at the level this one. The people saying that, wow, we are, the combining a number of battery systems to get, the commercial scale power plant. Yes, they can do, but the cost is way, way higher than this one. Then why don't we know them? Because we are not the customer. Why do we know the black panels? You could be potential customer. Interesting, right? Oh, this one is, I think this one is in Spain. So Spain, France, Germany, those are the main countries for this technology. And we are trying to, to catch up. We are not number one in this technology because there are not many customers. Everything is about politics. So they need to show something people know. So that's why, a lot of money in this country going into black panel rather than this one. Unfortunately. All right. So, okay.
You're about to help us play catch up? That like your goal here to help us play catch up with the rest of the country?
To do a research and development, R&D for this one, how many, the people do you think, in this? Thousands, tens of thousands. So it's all about collaboration. It's not something like, the Iron Man. One guy can do everything. There's nothing in the real world. There's no way one guy can do everything. Usually you need to collaborate with, the people all over the world to design something like that, to improve something like that. So I'm doing a very small part. What's going to be the material that we can use to store that energy? So we use a nanotechnology, trying to disperse nanoparticles, carbon nanotube, graphene, trying to increase CP value of a material, specific heat. Yeah, that's what I do. Interesting, isn't it? If you're interested, you already get into a lot. So go to graduate school. Go to graduate school. Getting a master's degree in engineering is beneficial. Getting a PhD in engineering, in terms of economic point of view, I'm not sure. So here's the thing: if you get a bachelor's degree, there are a lot of opportunities, but usually pay grade is a little less. If you get master degree, your market is getting smaller. However, the pay goes up. If you go to PhD, market is very, very small. Pay is high, but small. The competition goes up. So if you do very good, then you can go to PhD. I'm not sure. I want to combine with business altogether, economic, everything. And master is a good degree because you spend only 2 years rather than 4 years, right?
What's the best place to get it?
What's the best way? For master's degree, there's not much, the best places unless you go to PhD. So PhD matters because, that you need to find the right person. What about in this technology? How many experts are in the world? 1,000? Not many. Not many. 20, 30, 40. So if you want to study a particular area, you need to find the expert in that area and then go to their school. It's not about, the name of the school. It's about, who's going to be your advisor. On masters, there are two different masters. One is I want to work on an R&D field in master's degree. I want to, do a coursework in R&D, the master's, degree. So if you want to do, the coursework, you need to go to, there are many universities, that provide good coursework. Here in, the Michigan, we have a U of M, MSU, and there are many, the master's program have a good coursework. Sometimes you want to, establish your, the research capability. If you want to write a paper, then you need to find the master program that is focused on, the research. So it depends on, what you want to do with that. If you just want to, to get another 30 credit hours of coursework, then you need to find the school that has, the established coursework. If you want to, work in a research industry, then you want to, to write a paper while you are spending 2 years, then you need to, to find the school whose master program is, the research intensive. How are we going to find, master program in research intensive? If a school has a PhD program, all the researchers are heavily focused on the PhD program. If a school has only master's program, like us, all the researchers are on the master level, the programs. So if you want to do a research experience and then you only want to do a master's degree, you need to find a program that doesn't have a PhD program. Makes sense. One of my students who graduated 2 years ago wrote 8 SCI journal papers within 2 years. And then he got 4-year fellowship in NCNU, NC State University. That's not assistantship. It's a full, the fellowship. Is an international student. Usually those full fellowship does not given to, the international students. So it's all about, how many papers you can generate while you are studying within the time. Then, are we need to be really smart to work in engineering? Not necessarily. You just need to be very patient and work really hard. Because engineering is about, how effectively you manage your time. You solve more problems, you get more degree, the better degree. That's how it works in engineering, isn't it? We still have one more problem, so let's solve it. A Carnot heat engine receives heat from a reservoir at 900 degrees Celsius at a rate of 800 kilojoule per minute. Reject the waste heat to an ambient air at 27 degrees Celsius. The entire work output of the engine is used to drive a refrigerator. So we have a heat engine and a refrigerator together. We have a heat engine. This heat engine has 2 thermal energy reservoirs. One is at high temperature. The other one is at low temperature. And heat transfer direction is from high temperature to low temperature. So there's a Q dot H. There's a Q dot F. And we can produce power, W dot net. This power is going to be used to run a refrigerator. So there's a refrigerator is going to receive this heat, receive this power, and transfer heat from low temperature. Release that heat to high temperature. So there's a TR and there's a TH at the rate of Q dot H and Q dot F. Then the heat engine is a Carnot heat engine. So this one is reversible. That's good. Then how can you evaluate its performance? This is a reversible. So the efficiency can be determined by the desired output, W dot net, over required input, Q dot H. Or you can also say 1 minus Q dot L over Q dot H. And this heat engine is also a Carnot heat engine. That means this efficiency can be determined by this equation too. 1 minus TL over TH. Okay? And what about the other one? Determine the maximum rate of heat removal from the refrigerated space. When this refrigerator can absorb heat at the maximum rate. This one is a Carnot heat engine. What about this refrigerator? When determine the maximum rate of Q dot L. When you see the maximum rate, when that refrigerator is also Carnot refrigerator, reversible. So we can say from this word, we can learn that this one is also the ideal refrigerator, Carnot refrigerator. So COP of refrigerator can be determined by desired output, Q dot L, over required input, W dot net, or you can say Q dot L over Q dot H minus Q dot L. Then we can also determine this COP by reversible COP, which is TL over TH minus TL. So now we are ready to solve this problem. What is the temperature of the source of this heat engine? 900. So TH is 900. However, we don't want to use degree Celsius. So it's going to be 1173 Kelvin. At the rate of 800 kilojoule per minute. So Q dot H is going to be 800 kilojoule per minute. Rejects the waste heat to the ambient air at 27. So this one is 27, 300 Kelvin. Then the power produced by this heat engine is going to drive the refrigerator that removes heat from the refrigerated space at -5. So this one is -5, 268 Kelvin, and transfers this heat to the same ambient air at 27. So this one is 27, in other words, 300 Kelvin. Now we are ready to solve this problem. From this, TH is going to be 1173 Kelvin. TL is 300 Kelvin. Can you determine the efficiency? Yes. What is the efficiency? 0.744. 0.744. 74.4% efficiency. Then we know Q dot H, that is 800. So this one is 800 kilojoule per minute. What is the efficiency? 0.744. Can you determine the power? Yes. Power developed is going to be 595. 595.2 kilojoule per minute. Then this is the power that goes to this refrigerator. So this W dot net is going to be 595.2 kilojoule per minute. Then we know the temperature of the source, temperature of the sink of this refrigerator. TH is going to be 300. TL is going to be 268. TL is going to be 268. Can you determine the COP? Yes. COP is going to be 800, 8.37. If it is 8.37, can you determine Q dot L? Yes, we can. 8.37 times 595. So we get 4,982 kilojoule per minute. So this Q dot L is going to be 595.2. This Q dot L is going to be 4,982, and 800 minus 595.2 is going to be 204.8. This is Q dot L, and 595.2 plus 4,982 is going to be this one, 5,577.2. Now we have the rate of heat transfer in every direction. Then we want to determine the maximum rate of heat removal from the refrigerated space. This is the answer, kilojoule per minute. Then part B, the total rate of heat rejection to the ambient air. So there's a heat rejection to the ambient air, and there's a heat rejection to the ambient air. So altogether, this one and this one, the total heat rejection is going to be 5,577.2 plus 204.8 is going to be 5,782 kilojoule per minute. So that's the total heat rejection. That's all. Any question? Extra credit for what? Anything? Oh, that's a good idea. You have two more exams, exam number 2 and exam number 3. It is about 30%. So 30%, 30%, so 60%. We haven't checked the attendance yet. So that's a 3%. So you still have 63% not graded yet. So talking about extra credit, do your best on the second exam and third exam. Don't miss the rest of the class. You get 63% on top of what you already got from the first year. So that completes chapter 5. We have an exam coming up this Thursday, not today, a week today from today, next Thursday. 4 problems from chapter 3, 4, 5. But isn't it too simple to expect what's going to be? We all know what's going to be in the, from chapter 5. I just gave you this well-made summary right here. So there's at least one problem from this slide. And how many devices that we studied in chapter 4? Nozzle diffuser, throttling valve, turbine compressor, mixing chamber, and heat exchanger. You all know what are they, and you know how to make their energy balance equations. How many problems do you expect? 4? Among these 5, nozzle diffuser, turbine compressor, mixing chamber, throttling valve, and heat exchanger. And list 1, could be 2, right? Yeah, 2. And in chapter 3, what we didn't test, moving boundary work. So there will be at least 1 problem from moving boundary work. There are already 4. Now you know what's going to be in the second exam. Lower, okay. Moving boundary work. And this one. And 2 problems from chapter 4. And we know there are 5 different devices that we studied: noose, turbine compressor, mixing chamber, throttling valve, and heat exchanger. Pick two among them. So that completes chapter 5. And what comes next? The hardest chapter of thermodynamics. The hardest chapter of thermodynamics. Look at the name, entropy. Sounds very complicated. However, it is not. As long as you know what is entropy, if you can understand entropy, things are pretty easy. So from now on, for the next 20 minutes, I'm just going to talk about what is entropy. Then what is entropy? Sounds like similar, another thermodynamic property. Yes, it's another thermodynamic property, like internal energy U, enthalpy, specific enthalpy H. Now we have an entropy S. Entropy is S. Then what is entropy? Entropy is a thermodynamic property that shows how much useless energy is in the system. How much useless energy in the system. Then let's talk about, I have this much energy. 10 units of energy. So 10 units of energy is in this capsule. If it is useful energy, let's say there are 10 units of electricity. Sounds very useful, right? How do we know whether this energy is useful or not? Can you create energy? No. Can you destroy energy? No. You can only change the form. Then, when I say this energy is useful, that means you can easily change the form of energy from this to another. So now I have a 10 units of electricity. Is it useful? Can you change electricity to another form of energy? Okay, so let's say you have a motor. Can you change electric energy to mechanical energy? Yes. Now let's say you have an electric heater. Can you change electric energy into thermal energy? Yes. So changing electric energy to another form of energy is super easy. So electric energy is useful. Am I right? Okay. Now mechanical energy. So this one has a potential energy and kinetic energy. Is it useful? Yeah. If you have a mechanical energy, can you create heat? How? Mechanical energy. I just created heat, right? So converting mechanical energy into heat is easy. So mechanical energy is useful. Now I have a heat. This is hot coffee. Let's assume that it's a hot coffee. Can you create electricity? Can you convert this coffee into electricity? No. Can you convert this heat into mechanical energy? No. So is heat a useful energy? No. It is useless. So if you have a 10 units of energy, if you have a large portion of this 10 units is heat, then you have lots of useless energy. So if you have electricity, 10 units, it's very useful. If you have a heat, 10 units, even though they have the same amount of energy, heat is very useless. So how can we know one can has 10 units of electricity and the other can has 10 units of heat? One is useful, the other one is not. But if you only know internal energy U or enthalpy H, you cannot tell the difference. So here we introduce entropy. Entropy is a thermodynamic property to show how useless it is. So if you have a 10 units of heat, its entropy is very high. If you have a 10 units of electricity, entropy is very low. So if you convert this electricity into heat, entropy goes up. If you convert this heat into electricity, entropy goes down. Then, can you convert this heat into electricity? No. So entropy cannot go down. Entropy can only goes up from useful energy to useless energy. So once entropy increased, you cannot go back. Then we heard from the chapter 5, there's a reversible process, irreversible process. Irreversible process means a process happened and it cannot go back. Entropy increased, entropy cannot decrease. Yes, when there's an irreversibility, that means entropy increased. What about if it is a reversible process, can go back? Then there is no change in entropy. Electric energy, go to mechanical energy, go back to electric energy, mechanical energy. There is no useless energy is created. There's no heat is created. That means entropy remains constant. Entropy only increases when you just turn some of this useful energy into waste energy. What is that? When you create heat. So entropy can tell you how much heat is created, how much useless energy is just created from useful energy. That's entropy. So then let's assume that this is a very hot coffee. It's hot, 100 degrees Celsius. If I place this hot coffee on this desk, what do we expect? There's a heat transfer from the coffee to the surrounding air. So the coffee temperature goes down. Then, is it possible, can I, bring this, the coffee at room temperature, place this coffee cup on this desk, and this coffee is now magically absorb heat from the air and become hot coffee again? Like Dr. Strange. That's not possible because in that case, entropy goes down. When this hot coffee transferring heat to the surroundings, entropy goes up because hot coffee is more useful than warm coffee. So when you have hot coffee, the only, the direction of process is going to be heat dissipation to the surroundings because that's the direction when entropy increases. Observing heat from the surrounding, like Dr. Strange, is when entropy goes down. That's why Dr. Strange is a movie, not the reality. Because what he does is everything about entropy going down. Not possible. Then, okay, I get that. Whenever we, convert useful energy to unuseful energy, we increase the entropy. So, then, where can we use this information? If you can quantify the increase of entropy, if you have two different design directions, then one has this much entropy increase, the other one has this much entropy increase, then you can say this one is better design, this one is worse design because there's more irreversibilities because of the entropy increase. So if you can, calculate this much entropy can generate during this process, you can say how, the poor the design is. How many irreversibilities have been provided by the process. So if there are more irreversibilities, there's a more increase entropy. So finding, being able to calculate entropy increase, you can, improve the current design. Okay? Then, what do we need to know in this page? Only one. The definition of entropy. The change in entropy, S, is going to be del Q, the change in Q, divided by temperature T, when this process is reversible. That is the definition of entropy. Then you can say, oh, I get that, there is an entropy S, but I don't know what that means. It's simple. ds, the changing in entropy, is that. So if you want to calculate entropy change, you just need to integrate this one from 1 to 2. From 1 to 2. Then you can calculate the entropy at the final state after a process minus entropy at the initial state before the process. So you can quantify how much entropy has been increased during a process. Then finding this one, is it difficult? It's not. We are going to learn how to evaluate entropy change in a very simple way. And why this one looks complicated? Because that's how the people found entropy. So I'm just showing that from what is the formal definition of entropy and how people found entropy. Those are written here. Do you need to memorize them? No. What? We have to do entropy. We have to do entropy. Yes, but not as is, in a much simpler way, okay? Then let's talk about some characteristics of entropy. Processes can occur in a certain direction, only not in any direction. So that direction should be the increase of entropy direction. If I have a hot coffee here and place on this desk, we know there's a heat transfer from this coffee to the surroundings. It's just too easy because we learned that from our experience. But what about there is a complicated process? Then you don't know where this one should go. Then you can calculate how much entropy increases from here to there and from here to there. Then the direction is going to be where entropy increases. So if going this way, entropy increases. Going this way, entropy decreases. Then you can see, oh, this process should occur in this direction. Of course, this one is very simple. Placing a hot coffee on a table, we all know what's going to happen. But what about if the process is very complicated? Then you may not be able to know which direction this process can occur. What about if you are designing very complicated electronic devices? How can you know which process this should occur? You can only calculate that by entropy, rather than just imagine in your brain. That's where you can use entropy. Then, entropy is a non-conserved property. So there is no conservation of entropy principle. Okay, that's no problem. Then, is that it? Oh, there's no conservation of entropy principle, so let's not come up with any entropy balance equation. The end. No, that's not the case. If you know there's no entropy, the conservation of entropy principle, you can come up with another equation. What is that? Let's talk about energy balance equation. How do we write an energy balance equation? Because there is a conservation of energy principle. That means energy goes into a system minus energy goes out of a system is going to be the change of energy of a system. That we know based on conservation of energy principle. So now, can we do the same for entropy? I don't know, let's try. Entropy goes in minus entropy leaving the system should be the change of entropy of a system. Can we do that? Unfortunately, no, because there is no conservation of entropy principle. Then why entropy is not conserved? because we know when there's a process, entropy should increase. So you know entropy should increase whenever there is an irreversibility. Then, okay, entropy should increase. Then what about if I add another term that represents the increase of entropy plus entropy generation? Then this equation works. Then if you can solve this equation, what can you determine? How much entropy is generated? By using entropy balance equation, you can determine how much entropy has been increased by that process. And by being able to determine entropy generation, if you have, let's say that, that you're working for a company and that trying to improve the performance of, let's say, on electronic device, and there are 10 different, project teams came up with 10 different ideas. Then how are you going to choose what is the best design? What is the plan that you want to pursue? You can calculate entropy generation for plan number 1, plan number 2, plan number 3, etc., 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 etc. And the one has the least entropy generation is the most efficient way, so you can pick that one. Make sense? So that is based on the characteristics of entropy. So that comes from number 2 and number 3. Entropy is a non-conserved property, so there is no such thing as the conservation of entropy principle. However, because of that, we know entropy should increase. So we can add entropy generation into this entropy balance equation to be able to determine entropy generation. Make sense? Okay, so I guess some, a brief idea about what is entropy. So what we are going to do in chapter 6, we are going to study 3 things. First, used to be able to determine entropy. So we are going to study how do we determine entropy. Did we study anything about, the finding of property? Yes, in chapter 3, we studied how to evaluate specific volume V, U, H, etc. So we are going to follow the same. We are going to learn how to determine entropy S for a phase change material, like the table. So that's what we are going to do first. And then we are going to find entropy for pure system, pure gas, pure solid, and pure liquid when there is no phase change. So that's the first thing that we are going to do. And second, I told you that entropy only increases when there is an irreversibility. That means that when you design a turbine, when you design a compressor, when you design a heat exchanger, pump, motor, anything that uses energy, you can say when entropy remains constant, that's when the process is reversible, right? Because entropy only increases when there's an irreversibility. When the process is reversible, entropy remains constant. Then, when you design a turbine, let's say you want to design a turbine, the best turbine is going to be when entropy remains constant. But in reality, entropy cannot remain constant. But one thing that you can calculate is how close your turbine to an ideal turbine whose entropy remains constant. That is called isentropic efficiency. Isentropic process spins when entropy remains constant. When entropy remains constant, that's the ideal system, because entropy did not increase. In other words, everything is reversible because the device was ideal. Then actual system should have entropy increase, but some systems have higher entropy increase and the other system has lower entropy increase. So how can you, compare these two? By comparing your system against the ideal system, that is isentropic efficiency. Like for example, if you, buy a hybrid car, let's say Toyota Prius, how much gallon of gas do you need to drive from here to Midland? Less than a gallon, right? Now you are going to buy a dump truck. You want to drive a dump truck to Midland. How much gas do you need? A lot. For driving the same distance, why you need to, why you need to consume much more gases? Because the dump truck has much more irreversibility. So if you want to design an ideal car, the goal should be when entropy increase is minimized. Then you have the most efficient vehicle. Then you can drive from Mount Pleasant, Michigan with the minimum amount of gas. That is isentropic efficiency. When isentropic efficiency goes to 100%, that means that it is the most efficient in the system because entropy increase is close to the ideal system, isentropic system. The third one, finding SGen, entropy generation, by using entropy balance equation. Those are the three items that we are going to study in chapter 6. Okay? So we only have 3 minutes. Let's stop here. Next Tuesday, we are going to study how to determine entropy for phase change material and pure system. Any question? No? Then see you next week.